Hi everyone. So today I'm going to talk a little bit about everything, and when I started putting this together I wrote up something Øredev, and then I forgot about it for 3 months, and then I got welcome, you're invited, and I have to look it up and see, okay, what am I going to do? Yes, I know about these things, but before we begin, I'm really curious about all of you guys. So I want to ask, who are you people? And perhaps first and foremost, I want to ask, are there any biologists or neuroscientists in the crowd? I see no hands raised. That is perfect. I can say whatever I want and you cannot complain. Who am I then? So my name is Linus, and for the past 5 years or so I have been working together with neuroscientists at Lund University building a company called Intuicell. And there we do essentially brain-inspired artificial intelligence, where we do away with everything we know about AI and instead use what we know about neuroscience and biology to make things learn. Other than that, I do a little bit of everything. Founder, hacker, nerd, circus artist. I do fire eating. We talked about that just before. And in Swedish, you'd perhaps call me somewhat of a mångsysslare. But never mind that. Today, we're going to have a quick, simple 3-step presentation. First, we're going to go into a bit about what is the meaning of life. Then we're going to continue with how does that get better with a brain? And finally, we're going to round off with, is this the same thing as AI and deep learning? And easy topics, I know. So let's start this up, right? So what is life? And to answer this question, I did what we all do when we have deep, interesting questions. I asked Gemini. So to be considered alive, an organism must exhibit several different criteria. First and foremost, cellular organization, then reproduction, growth and development, yada yada, and so on and so forth. And I was thinking as I looked at this, if we squint a bit, if we don't look too closely and see cellular organization, all living things are composed of one or more cells, well, we can rephrase that a bit and be less biology elitist, if you will, and say, well, there's something with a boundary and an inside that's different from the outside. And if we look at reproduction, I say, well, perhaps that's not relevant, because we can see things like sterile work bees that don't reproduce, but we absolutely consider them living things. We can look at growth and development. The organisms grow and change throughout their life cycle and say, well, something can maintain this difference between the inside and outside despite the shape of that surface changing over time. Energy use. Living things need and use energy and sustain themselves, known as metabolism. Well, actually, something can recover resources that it uses on the inside from the outside. Then we have homeostasis. An organism must maintain a stable internal environment despite external change. Something has tools to maintain, again, its inside despite the outside. Response to stimuli. Something has tools to react when the outside changes. If we poke something, it responds to that poke. Adaptation, finally, it's said here, over generations, populations of organisms adapt and evolve in their environment. Again, it's the same thing here. Something can maintain itself despite changing over time. So if we squint a little and look at all of these things, aren't they all pretty much the same? So what is life then, if we look at all this? And if they're all the same thing, we know this from biology, that usually the important word in a throng of words in a biological sentence is the most complicated one. So we ask, what is homeostasis anyways? So again, thinking deeply about this, I found the facts and I brought them to you. I'm not expecting you to read all this, especially because it's so small here, but I'll pick out the nuggets here. Homeostasis is brought about by a natural resistance to change, as we looked at before. And most importantly, perhaps, if homeostasis is successful, then life continues. This is super interesting. This is what we want. It means if homeostasis fails, we are no longer alive. So how does it work then? Well, jumping in a bit here, the central motivation for all organic action, it's composed of 3 interdependent components for the variable being regulated. Okay, so there's a variable involved. There's a receptor, something we call a control center, and an effector. So we have a system composed of something that takes in something that reacts when it takes in something by making some change on the outside. So if we start squinting again, and if we look just at these important parts, it's a central motivation for action. It's 3 interdependent components. We have the receptor, we have the control center, and we have the effector. And then we can perhaps imagine other things that fulfill these properties. So I thought a lot. I imagined this. We have a house. Something goes into the house or something affects the house from the outside. We have an action that the house can do to essentially restore that parameter to the equilibrium. And I wanted to exemplify this. So I thought, okay, how about temperature? So temperature affects the house from the outside. We want to maintain our stable 21, 22 degrees indoors, as mandated by the BRF I live in. And if that changes, we effectuate or build up a system to regulate the temperature and get it back to the original state we wanted it in. So the temperature goes in, it's measured by a thermostat, and then it either turns on the heater or it turns on the AC with the intent of returning to the target temperature. Interestingly, of course, this can be an automated control center. If it's cold, then enable heater. If it's hot, then enable AC. Or it can be a manual process with a person walking through the house when it sees that the temperature is cold and then changing or turning on the heater to get that back on. But interestingly, this is a homeostatic process, no matter if it's automated or if it's manual. And I had to ask myself for a very long time, is this life? So I went back to Gemini's criteria, and I realized that maybe if I squint really, really, really hard, then this homeostatic life house can be considered living. But of course, this is perhaps not what we think about when we say living organisms. Instead, let's try to identify something simpler to talk about. Let's talk about single-celled organisms. And I wanted to find the perfect example for you guys of a single-celled organism. So I did what I always do, and I got my answer. This is a sample of, I don't actually know the name of this cell, but we're going to use it anyways. It has a receptor. It can be hungry. It can have a lack or deficiency with respect to its internal environment. And when that receptor goes active, it can respond by engaging an effector to take in and restore that parameter to a natural equilibrium. Essentially, it's a quick and simple implementation that says, if I'm hungry, then I eat. And the homeostatic life form can have many of these. If there's no food, then we have another effector we can use to control that system. And we can just extend our control center to make this work and, in effect, regulate these parameters back to their natural homeostatic equilibrium. We move all the control parameters we have back to the state where the being survives. In biology, it looks like this. Whenever we engage a receptor, the receptor has a set of chemicals on the inside of the cell boundary. And as the receptor is engaged, it releases those chemicals into the internal environment of the cell, whereupon they reach an effector, and then ideally the effector will restore the equilibrium state in the internals or external environment, thereby canceling the receptor activity. Now, if we come back to this, we realize that the homeostatic system in the single-celled organism, much like the house, isn't going to be very good at keeping the single-celled organism alive. Because we can be in a house, the house can be functioning, it can be functioning because we help it, and then the power goes out and suddenly the homeostatic system doesn't work. We can take the single-celled organism and put it in a saline solution, and suddenly the homeostatic or single-celled organism dies, because no matter what action it does, it won't be able to restore that homeostatic equilibrium. So really, it's just actions responding to needs, and no one said they had to be any good. And that begs the question, are both of these things alive? Now, let's try to think a bit more about this and perhaps move into more complicated organisms. If homeostasis is a basis for things being alive, then what happens when it gets harder? Well, it's still much the same process as we had before. We start by adding some receptors, some effectors. We engage a control system with this so that they can affect each other and return to equilibrium. Here it's no longer a heater and a cooler. It's being able to move to ideally an environment that's more suitable. And we can keep building on this. If we need to ingest chloride, we do that. If we have too high internal pressure, we can expel chloride. And we can keep building on these systems and connect them together to build a life form that just diffuses chemicals internally to essentially generate an organism that survives. And it's cool because even though we're adding all of these things, it's still quite a scalable process. And here we exemplify this by saying that each receptor just has a unique chemical or protein that it's emitting internally that allows the organism to activate an effector that has the desired result in some sense. So, meaning that the organism will simply survive given that the right effector was engaged. So, given that we can consider homeostasis for very simple single-celled organisms, complicated single-cell organisms, what happens when we scale the homeostatic process? What happens when we make the life form bigger? So what we get to then is multicellular life. And with multicellular life, we are starting to touch on this: is the agent or the homeostatic life form suitable and capable of surviving despite its environment? With the single cell, we could perhaps pick it up and put it in an unsuitable environment, but the bigger this organism gets, the harder it will be to affect it in that way. And the more tools it will potentially have, the larger scale the tools can potentially act at to remedy these homeostatic issues that it's experiencing. So with the larger organisms like the volvox, we can see this happening where we have a single type of cell being replicated across a boundary for a living organism. And now we have many copies of one cell, meaning if one dies, we can still consider the bigger organism alive until a sufficient amount of them disappears. We have internal storage where essentially if the external environment isn't providing food, we can still sustain the organism by having a storage of necessary chemicals and other reagents for survival internally in the cell, much like we do in our bodies. And we can do things like synchronized action, where instead of acting at the nanonewton scale, when a single effector is generating an impulse that affects the environment around it, we can perhaps go up to the micrometer scale or the Newton scale or the millinewton scale and make much, much bigger changes to our surroundings. And finally, many cells enable us to specialize, meaning each individual cell can perhaps be much, much better at generating that same action in the environment. And by making use of other friends that are also specialized in the larger cluster of cell or the organism, we can have better receptors, we can have better effectors, and we can have a more specialized control center to control that. But there is a problem with this type of scaling going on when we go from single-celled organisms to multicellular organisms. And it's one of the topics we touched on up above, synchronized actions. Because when we expect an action to be synchronized, and the process that is occurring with is us releasing chemicals that diffuse through an environment, then as the scale of the system increases, we are still sending out single, small, or minuscule amounts of a chemical that we intend to reach a specific effector. And as the distances increase, it becomes slower and slower as a process for the chemical gradient to reach the effectors. Not to mention, we have a limited number of individual molecules being sent out, meaning it can reach different effectors at different times, so it won't really be synchronized. And perhaps first and foremost, it will start becoming unreliable. The single chemicals we send out might miss some of the effectors we send it to. And first and foremost, if we want to remedy that, it's going to get increasingly costly in the amount of chemical we have to release. Imagining, for example, us releasing a chemical at the level of our feet and having that diffuse through our body to reach our heads. It's a process that could take, in some cases, several minutes, if not longer, and that will not be suitable to be able to effectuate actions that relate to whether or not we survive in the short term. So if only we had a fast, scalable, and reliable way to transmit these signals across large distances to reach suitable effectors. I wonder what that type of, so this is where the neuron comes in to the biological system. Because what the neuron does as its core is take a chemical gradient that is present inside the neuron, convert that into electrical signal, a binary almost electrical signal, that then can travel across these long pathways to reach what's called a synapse, that is a connection to another neuron or another cell, whereupon it can be converted back into a chemical gradient. And if that second cell is a new neuron, or if the second cell is something else, that cell can then react much in the same way as if the problem has occurred in the local environment instead. So, of course, these neurons, they don't work in isolation, but they work together with receptors that then take some other effect that happens across our bodies. It can be a touch response. It can be a temperature gradient across our skin. It can be the vibration that happens within the cochlea, or it can be the fluid movement that happens within the vestibularis. The cochlea, of course, being the inner ear, whereas the vestibularis is the balance organ within the brain. And it converts these changes that are experienced there into a chemical gradient through a homeostatic process, sends it through an axon to a neuron, to another neuron, to another neuron, to another neuron, through these large networks. And by having that measurement being in a homeostatic environment, we can consider this a receptor in that same domain. Of course, these two can't exist in isolation either. They need to affect the environment somehow. So in the end, all of these signals are passed through different cells, and they reach an effector. And in biology, the most common, the most well-known effector is the muscle we use to now no longer control the world at a nanonewton or millinewton scale, but at several hundreds or thousands of newtons to lift heavy objects and control the environment. Still, again, acting towards these homeostatic errors that came in at the receptors in different parts of the body and at different times. And through all of this, we can see that the homeostatic process that we started looking at with the definition of life and the single-celled house and life form is a process that is scalable and present not just in the individual cell, but all the way up through different and more complex organisms. And we even have the control center in the middle that lets the network here decide which actions give the best result. So interestingly then, when we have large neural networks in biology, we let the networks decide which actions give the best results. How is that process occurring? And this is where we start looking at the differences towards what happens in deep learning compared to biology. Because in learning, we have a system where a single receptor or a single neuron might connect to another neuron. And the big thing that happens is that over time, the signal that traverses these edges in the networks reach some neurons and ask, is this neuron that I'm connecting through via this axon, this long line, and the synapse, making the problem that is experienced by the receptor worse or better? And if the receptor infers that the problem is becoming worse over time, perhaps by signaling more strongly, then we know that the connections it reached out to are suddenly behaving badly for it, so we should dampen those connections. And similarly, if we see that we activate a receptor and rapidly the signal that came in goes away, we know that what's happening is going well, so we should make sure that the connections we have already established are maintained in a suitable way to ensure that the homeostatic signal we received at one end is transmitted meaningfully through the network to the other end. Adding a few more neurons to this, we get to what we all know in here. We get to brains. And a brain isn't just what we have up in our head, because a big life form like a human or a dog or even an insect consists of a spinal cord. It consists of a central nervous system. It consists of a peripheral nervous system that connects receptors to neurons to effectors. And we can envision this by saying a signal comes in at some input. And then that signal traverses through this neural network from the sensory environment or from the sensory point to the spinal cord, from the spinal cord up, in this case perhaps through the cuneate, which is a nucleus in our brainstem, into the thalamus, where it goes through the neocortex and then loops back into the thalamus and mixes with other signals. Then from there, it travels back down again, and that result is sent to an action. Now, what we can see from this is that this process is very similar to what we'd expect from deep learning. A signal comes in, it travels through a network, it mixes with other signals, and then it comes out and generates an action. And then we do something with that action. But what's interesting is that now we're not looking at this through the homeostatic lens. And if we start doing that, if we think of this central motivation relating to being alive, then it's no longer a signal, any signal that comes in as an input to our learning network, but it's actually a homeostatic error, something that might have an effect on our chances to survive. And it doesn't travel through the network just for any reason. It says it's rather, if we can't solve a problem locally, we pass it onwards. And we can see this in our own behavior when we react to reflexes, where it's not a process that necessarily goes on within the larger part of a brain, but a signal that comes from a receptor close to our knee, straight into the spinal cord and back again, reflecting in a quick action that we didn't necessarily feel that we had immediate control over. But if it can't be solved locally, if it travels upwards, it mixes not with any signals, but with other problems we're experiencing. And the actions we decide on as part of that aren't any actions based on the data we have, but actions that relate to the biggest problems we are currently experiencing. For example, if you hit my leg, I might react to that. If you hit my leg whilst my hair is on fire, I probably would not react to hitting my leg, because we are prioritizing different problems against each other and adapting our focus to the problem that is most relevant to the environment we're in. When you're in these stressful situations, you get tunnel vision. You can't hear what people are saying. You're stressed. No, you're focusing on a bigger problem that you might be generating internally as a result of other problems, or another feature of your environment that you have taken in that is more important than the things you're seeing right now. This is what we at Intuicell think of when we talk about how learning works within biological brains. And this is how the two compare to each other. And what's interesting is what happens when you start thinking about this in a learning process. With deep learning, we send the result to an action, and what happens after that is we score the result to get an error. And then we pass that error backwards through the network in a process known as backpropagation. And through the network, we compute derivatives to update weights throughout the whole network, and ideally try to understand, given a set of signals, how should we act to essentially behave in line with the error we received. But with brains, this changes, because we are not sending a signal backwards. Rather, we are sending a signal forwards through time. The effector will generate actions that engage the receptors around the rest of our body in new ways. And the change, the amplitude change in these receptors will traverse the network from a chemical gradient, through an axon, through a synapse, back to a chemical gradient. And at that synaptic junction, we can make weight changes depending on whether we, at that now decentralized and distributed location, see that the behavior, the amplitude of activity in that region is getting better or worse. And that will, in turn, connect back to the effectors and allow us to understand, are we actually solving the errors we are experiencing, or are we making them worse? Are we managing to stay in a region of state space, if you will, where our problems are all sufficiently small that we can ignore them and let them be? Or is every action we're doing pushing us outwards from that safe space? And if so, we need to make larger changes to the way we think to essentially survive in our environment. Let's review. First, we have deep learning, where we say we send a signal forwards and then we send an error back. Whereas with brains, the signal is the error, so we only pass it forward over time. With deep learning, we learn to find good target values. It's not any value. Actually, we don't know what good target values are until we're provided these error signals from the environments. Whereas with brains, we always have this error signal present because we design our sensors to enable that data to be present. And this allows us to think of learning not as finding good values, but remaining at good values, which is very different in terms of the learning process. Next, signals pass through the entire network in deep learning. But with brains, signals are passed from neuron to neuron. And this is a process that takes time because the propagation of a signal that occurs in our peripheral nervous system in our foot that travels all the way up through the spinal cord to the cuneate, it can take tens of milliseconds to arrive. And the process of passing from neuron to neuron is slow, but it's integrative. So we can have a signal that comes in at a photoreceptor in our field of vision that travels through the bipolar cells, travels through the retinal ganglion cells, then goes into the thalamus, then goes up to cortical cells, then passes through the cortex and comes back to affect some other part of our body. And that can take hundreds of milliseconds. In some cases, that process of the signal traversing continuously within our brains can take seconds, it can take minutes, it can take days and years, because something we hear or see affects the way we think. And that is not just a weight change, it's not just activity that traverses through the brain, but a combination of both that then produces the way we act in the future past that point. Finally, perhaps the most important thing for all of us interested in deep learning and AI today is that with deep learning, we learn, and we are only capable of learning when these error signals are provided through an external system. But with brains, again, everything is an error. And that means there's no difference between inference and training, because those same signals are always present. The difference, however, is that we have to design our sensory input to our system to enable that to occur. Finally, in summary, I want to mention a bit about what we've talked today. I forgot to start the timer, so I have no idea where I am on time. Perhaps someone knows. But in summary, first we talked about how a thermostat and a house might be alive, and took a very quick look at unicellular and multicellular life. Next, we reasoned about why neuronal networks started forming in the first place, why diffusion became such a slow process that we needed another way to communicate within larger bodies, and how scale connects that to the development of brains as we get more and more sensors across our body and need to integrate that in different ways. Finally, we reviewed learning in the brain through a homeostatic lens and compared that to deep learning and the contemporary artificial intelligence we see so broadly spread in the field today. Coming from this, I think I have a couple of minutes left to take questions, about 8 or so. So if there's any questions, I'm open to that. Otherwise, praise can be sent to my email address. And this is my colleague. You can send any complaints to him. Thank you. Any questions? There's one on the front.
In the brain, you also have reward sensor or reward stimulus, like you feel good.
Yes, you feel good, but you could also argue that the only thing you're doing is amplifying or damping activity in different parts of your brain. So what we call the reward center is a center that generates a neurotransmitter called dopamine. And it does that much in the same way as other neurons. There's a single neuron, it sends an electrical signal through an axon, and then it generates a neurotransmitter at the end that passes through other neurons. The only difference between the other neurons and these neurons is that what's emitted isn't something that causes an electrical signal to pass forward, but another chemical that makes the receiving neuron react in a different way. And that could have an effect on learning. It could, so to speak, make us feel good, but feeling good is also a way we have learned to react to different ways of engaging with the environment. It's not something that's built into us, and nothing is really proving that the dopamine signal being transmitted is what causes the learning, but rather that it's affecting the activity in the receiving cell. And that, of course, could in turn be, let's say it's a multiplicative change, then that multiplicative change could be affecting the learning process itself. One in the back. Mm? Yes, yes. So one interesting thing about the networks we build at Intuicell is that we don't need to randomly initiate our networks. They all start with 0 weights. And the only thing that we initialize is the random connectivity of the system. We structure that to enable different pathways to arise within a larger system. And that's the same thing that happens within biology, where we generate how do I say, so our genetics generate growth patterns within, both within the central nervous system and of course everything else that relates to the genesis of our body. And those processes, of course, we need to implement as well to make sure that the connectivity exists to enable different processes going on in the brain. But those don't need precision, because when you learn with homeostasis in mind, then you can actually have randomized connectivity with loops and cycles in ways that cause chaotic behaviors in deep learning. So with RNNs, if you try to have an infinite tail of activity, you start having problems with the learning because you can't propagate it far enough back. That's not a problem with homeostasis. You just look at, is there a positive cycle of activity occurring within a network? Then we can dampen that whole cycle, and that behavior will go away. It can essentially self-regulate within the homeostatic process across neurons as well. One over there. So what we are publishing right now, there is a video from back in March or so. We learned to make robots understand and control their own bodies. And we have used that in a demonstrated video to make a quadruped stand up and balance on its own. And primarily or more importantly, doing that learning process in the real world rather than relying on a simulation and a scaling across thousands of simultaneous simulations. I think maybe a final one, and then I'm out of time. Yes?
So you compared actual brain network to, I don't know, artificial one.
Yes.
And it seems like doing the learning process nowadays with the artificial ones, we trying to calculate the number of neurons on each layer and kind of create the network so it could solve a particular problem. How does it come? Like our neural network, it's somehow fixed, but on the other hand, it could adapt to the problem itself and basically find a solution to multiple different problems, sizes of the problems, etc. And with the artificial networks, we still have this huge problem that the network should be aligned with the problem itself.
Yeah.
Do you work on it in your company?
I don't work, I can't say we work specifically with alignment of data, since we work mostly within this homeostatic domain, if you will. But it's interesting thinking about how these two systems differ with respect to each other. Because when you start scaling up deep learning models, when you start introducing more data to them, and when you start training an LLM, you are essentially training it on more and more data. And you're telling it what's right in specific points of this whole space of different potential data it could act within. And you could argue that alignment is then a process of getting it to act in a specific way given some subsets of that data and hope it generalizes. But when you learn in a homeostatic system, and especially when you learn continuously, it's no longer that you have to be aligned before you train or before you finalize the training, because the system you are training, it can continue to react to how people behave around it, and therefore improve its behavior with respect to the receptors that you're providing it with. And if some of those receptors are then connected to alignment themselves, and their activity increases when the robot is, or the AI agent is behaving in a way that's outside what we perceive as aligned, then that can be a learning signal in itself, as long as we can understand and measure it whilst the agent is active and engaging with its environment. Thank you, guys. Thank you, everyone.